A graduate of computer science from University of Toronto, Vicky has been working at Shopify for the last 5 years, both in Toronto and Berlin, in data platform engineering, focusing on data ingestion. The title of her talk is Apache Iceberg, Merge on Read, Streaming CDC. Please welcome Vicky Bukta.
Hi everyone, I'm Victoria. I'm a staff data engineer at Shopify. If I could change one thing about my job title, it would be to insert the word platform. So I like to say I'm a data platform engineer. And I say that because I don't do all the modeling and kind of the fun stuff that people have been talking about today with data science. I don't transform data, but I'm there to build the platform so that other people can transform data and do analytics and do that sort of stuff. So I work at Shopify. If you have not heard about Shopify before, that's okay. We are one of the biggest commerce companies in Canada. We're Ottawa-based. And I use the word commerce instead of e-commerce because we have a whole breadth of different products. So our main product is the storefront. We have an online storefront, but we do all sorts of things from like shipping to inventory management and beyond. Now, my title has a lot of different buzzwords in it, but I'll go through each of them throughout the presentation. So I'll talk about the team that I'm on. I'm on the Lakehouse team at Shopify. I'll talk to you about what that is, what our mission is, our legacy system for data ingestion, the new system that we designed, the result of that, and kind of some closing thoughts. So I'm on the Lakehouse team, and you're probably wondering what is Lakehouse, what does that mean? But my team is responsible for providing Shopify developers with an interoperable, performant, and standards-based Lakehouse where first and third-party data can be ingested. That's a lot. But basically, the first part is the standards-based Lakehouse. So my team is responsible for setting the standards of how data is stored and kind of the life cycle of data on the platform. So that's the first thing that we control. The second thing that my team is responsible for is the ingestion of data. So if you think about the data funnel of the platform, so we're the first place where data comes into the platform so that it can be analyzed. And today, I'm going to focus on the first party ingestion of data. So this is specifically the raw data from like the production database. So how do we get data out of the application databases at Shopify and into the data lake so that it can be analyzed? So one of the data sets that my team is responsible for is producing something called a table snapshot. And a table snapshot to us means the state of a data source at a specific moment in time. So this is the pure replication of, let's say, the Shopify Shops table. So Shopify Shops, the application table, we want to copy that one-to-one in our data lake so that it can be analyzed by data scientists. And a table snapshot consists of one row per primary key. So this is not like an additive table. This is something that's being transformed. There's upserts being performed. And we always have the latest version. We want to have the latest version per a primary key. So our legacy system, we did this using batch data ingestion via statement-based replication. So what is statement-based replication? So probably a lot of data engineers, this is how you started replicating data so that your data scientists could analyze it. You did a select star from table. Select star from my table, take the whole thing, copy it from the production database, put it in something like Redshift so that people can analyze it. So this is a great starting point, but this doesn't scale for larger tables. And as well, like when your tables get very, very large, these queries become longer and longer to execute. You're more prone to failures, let alone putting extra load on the production database to even execute this in the first place. Okay, so we want to iterate on that. Let's do something a little bit better. So we can move to doing something like incremental. So we have something on the table called an incremental key. So the contract between us and the app developers is if you update this key, it means this row has been updated. There's a new version of it. So the way that we collect data from the table is select start from table, where updated at, that's our incremental key, is greater than this timestamp, the timestamp of when I last extracted. That's the contract. But one of the big problems with this is there's a possibility to miss updates. We have this contract with the app developers that they have to update this field to tell us that the row has been updated. Unfortunately, that doesn't always happen. Shopify is so big that there's lots of cases where their application just doesn't do this. So we're missing updates, and data scientists don't like that. We're like kind of the middlemen of moving stuff from point A to point B. Data scientists come to us being like, the data is different and I don't understand why. All I can tell you is I don't understand why either. Ask the app developers, and no one likes that. So at some point, this also didn't scale to just do pure incremental, so we had to break it up even more. So we did these queries, which we called like bucketed queries. So we added this other clause to say greater than the last primary key that I've seen, order by primary key, take a chunk, take the first 10,000 rows. So now I have all these queries. They're much smaller, they're more successful, they're more likely to successfully execute, but I have to also run them sequential, which is not great. And one thing I want to point out about all of this, like I could rewrite this query to maybe be even better, but I can't actually ask the database what's not there anymore. I can't ask for the deletes. So I can ask for all this data, but there's no way for me to actually capture the deletes without doing that first query, select star from table, or having to re-ingest the whole table and like compare the results before and after. So this is really, really problematic for our data scientists. So that was all about the ingestion portion, but even after we extract that data, we have to actually produce the snapshot. So to do this, we have a Spark process. It's basically like a big window function that runs, take the latest version of the primary key based on the updated at or incremental field. But this is an expensive operation, and I'll go into a little bit about why. So we store our data in the data lake in Parquet format. If you're not familiar with Parquet, it's a columnar format. And what I mean by columnar is that the column data is co-located together. So what I have here on the side on the right is the spec of like what Parquet actually looks like. So I have column A, I have all the data for this file for column A co-located together. So I have the benefits of locality. And then I have all the data for column B, column C, and so on. If I want to modify this file, I basically have to throw it all into memory and insert in multiple places the change. So if I want to insert just one row into this file, it's not like adding a row to a CSV. There's multiple places in the file I actually have to do the insertion. I have to put the column A value in the first block, column B value in the second block, and so forth. So this is expensive. So columnar files are basically immutable. I have to basically overwrite it. This is an expensive operation. It's not great. So this started to just cost a lot of money and take a lot of time. So when building our new system, we had a bunch of different goals in mind. So first, we wanted to have a more scalable ingestion platform. We wanted to have a more scalable snapshot production. We wanted to have more accurate updates so that we didn't have this issue of like the app developers not updating the updated at field, and then we don't get the update. We wanted to be able to capture deletes, and we wanted this whole process to happen in under an hour. So we wanted to be able to publish new versions, new snapshot versions of our tables in at least an hour. So this is what we came up with. Streaming data ingestion of change data capture via Kafka written in Iceberg v2 storage format. So that's a lot, and I will go through each section of this. So first of all, change data capture. What is it? So I'm not sure how many people here are familiar with CDC or change data capture, but the idea, the principle, is to capture every single state change of a data source. So when it comes to your relational database, at Shopify, we use MySQL. MySQL has something called a bin log or binary log, which is basically an audit log of all the transactions that are happening to the database. So you get an event for every create, every update, every delete. So we have each of these as events. So there we go. That's our more accurate updates, and we actually capture the deletes. So we basically use this technology called Debezium. Debezium is an open source piece of technology. We use it to tail this bin log and emit the events to Kafka so that they can be ingested later on. Maybe you're wondering why we don't just write this down to disk right away. We put it into Kafka because there's a lot of other applications that are using this data. So it's a kind of a centralized store. But anyway, so we emit these events to Kafka, and now we can ingest it later on. So we built a tool called Pepto. Pepto is our tool for all of the ingestion needs at Shopify when it comes to consuming from Kafka. We consume these CDC events off of Kafka and write them as Parquet files to disk or to our object store. And we register them as an Iceberg table. Now, I'm not going to go into the Iceberg thing for a moment. I'm going to gloss over that. I'm going to come back. But basically, I've set up this pipeline now that's reading these events from Kafka and writing them down in my data lake. And with this, we were able to achieve scalability of ingestion. The reason for this is because I can control how many partitions my Kafka topic has. For each partition, I can have independent writers, so I can have X number of writers depending on the volume of that topic. I have more accurate updates because of CDC, the CDC data, and I have more accurate delete capture. Frankly, I just have delete capture now because of the CDC events. And for this to run, we can publish new data in the data lake within 7 minutes. So I've solved the scalable ingestion, the more accurate updates, and the delete capture. So now I'm going to take a moment, go on a tangent, and talk about Iceberg and what Iceberg is. So maybe you've heard of it. Apache Iceberg is a table format. And by that, I mean it's a convention, it's a library of how we represent data on disk or in our object store. And basically, it's a collection of metadata files that represents and points to the data on disk. And one of the best analogies I can give for Apache Iceberg is a file system. So probably a lot of people here are familiar with what a file system is. It's a collection of pointers so that I can relate to the data that's on my hard drive. So Iceberg is something similar. It's a collection of pointers to the data in the object store. So maybe you've seen this diagram before. So I just want to illustrate here that it's basically just a collection of pointers. We have all this metadata pointing to other metadata files that contains information about the data files on disk. And the promise of Apache Iceberg is to give us a metadata-rich table format on top of the Parquet files. And the goal of using all this metadata is such that an engine can come in, like Spark or Trino, maybe Flink, and they can more efficiently perform file pruning. So that will give us more scalable reads and more scalable writes, because I can find exactly the data I want to pick up or the data that I want to modify on disk. So our thinking was to use this to scale the snapshot production, and the goal of having snapshot production in under 1 hour. So there's a lot going on in this diagram, but basically what I wanted to demonstrate here is that we have the first diagram that I showed of writing the Parquet files. Basically in Iceberg, my Iceberg format, I have metadata that's just pointing to this Parquet file that I wrote to disk. And the power of Apache Iceberg is the metadata, of course. So what metadata does it actually hold? So in the Parquet file, in the header of the Parquet file, there'll be a bunch of statistics. Statistics about the upper lower bound of all the columns, maybe some aggregated count metrics for the different columns. So all of this data that's in the header of the file is actually aggregated. It's in the Iceberg metadata. So this is the magic of how Iceberg gives the engine all this information so that I can do more efficient planning. So now I'll get to the merge on read part of Iceberg. So in the second version of the Iceberg spec, they introduced this concept of delete files. And what a delete file is a way to communicate data to be updated without actually modifying the files on disk. So I could have this like append-only format that's actually going to perform upserts at query time. And the way it does this is by introducing these two different kinds of delete files, one called a positional delete and one called an equality delete. A positional delete refers to a specific file and row in a file that I would like to filter out. Then an equality delete, I write in there the rows that I would like to match, or like the column values I would like to match I want to filter it out. So it's the combination of appending new data files with these delete files that I can actually perform an upsert. And I'll get into how that actually works in a little bit later. But the goal here is to basically procrastinate the rewriting of data files on disk. Because remember, Parquet is expensive. Parquet columnar files are expensive to rewrite. This is our core problem. So by procrastinating rewriting data files, I can do more efficient like rewriting and compaction production of our snapshot later on in the future, after I've collected, I don't know, X amount of updates. And also because the rewrites are more targeted, I can specify the specific file, specific row I want to filter out. The goal or thinking was that this would also help reduce compute. Yeah, so this is basically it. So the promise of rewriting these files and reduce compute, our goal was to have more scalable snapshot production. Okay, so here's an example of, say, a base table that has two rows. I have ID 25, ID 30. Then I was consuming data on Kafka. Here's my new Parquet file that I ingested. I have a new version of ID 25, and I have a new row that's coming in, this ID 45. I have a create, I have an update, but I only want to show the first one. So what I want to be able to perform here is I want to filter out from my base table the original version of ID 25, and within the data file itself that I wrote, within it I want to filter out that first version of ID 45. So the first thing I do is I'm going to append an equality delete file. And in my equality delete file, I add all of the IDs that I saw in my data file. And I do that because I know that I have a new version for all of those primary keys. So when I do this, so 45, there's no 45, new 45 version, but I have a new version of ID 25, this gets filtered out. So the next step is to append my new data file. Here are all my new updates, but I still have the duplicate within that new data file. And finally, the last thing I want to do is do that filtering of a row within the data file itself. This is where the positional delete comes in. So I can specify the Parquet file, the position, so I want to get rid of that second row. And after doing that, I get my desired result. So I'm removing that duplicate within the data file itself. So these delete files, they absolutely have an effect on the query performance, because instead of rewriting the data files on disk, I've pushed that operation to the engine. So it's doing it in memory at read time. And what we noticed right away was the positional deletes are very, very targeted. I'm specifying the file and the position, the file that I want to filter out. So that's really, really fast. What's slow are these equality deletes, especially when you have a row that's getting constantly updated. It might have to touch lots of different files on disk to actually perform the update. The other problem with our approach was that it was creating lots and lots of small files. We're a streaming platform. We've built a streaming tool to be able to do this. But Iceberg allows us to do maintenance after the fact, so we had to run regular maintenance to rewrite the data on disk periodically. So the result of this was, like I said, we had the under 7 minute ingestion time, but also we were able to produce this new snapshot when we actually rewrote it on disk in 3 to 40 minutes. Depending on the size of the table, right? But even though we were able to produce the snapshot for our biggest table in 40 minutes, what we realized is that actually we had a lot of levers in our control, and theoretically we could have actually gotten it down to about 7 minutes if we really wanted to. And that's because of all the different levers that we had at our disposal now that we didn't before. So number one was the parallel rewriting. So partitioning is your friend. If you can figure out how to partition your data so that you can reduce the number of files you have to pick up to do the rewrite or do the comparison, this is great. So we partition by Kafka partition. So maybe this means increasing the number of Kafka partitions for your topic, and I'm able to parallelize that rewrite. The other thing that Iceberg offers is a configuration called max file group size. So it will basically create these smaller tasks to do smaller targeted updates instead of putting it all into one big task. So, and then finally the machine size. So I can always control the machine size of the workers on my cluster, my Spark cluster, to actually do the compaction. But I have way more levers that I can play with, where before, when I was doing the rewrite, when I was doing the snapshot production, basically the only tool that I had at my disposal was increasing the machine size. So we now were able to produce the more scalable snapshot production, and we were able to produce that snapshot in under an hour. So we've checked all of the boxes. So I'll go over some closing thoughts. So one thing that we noticed right away was there's sort of two different ingestion modes here. So there's the initial ingestion. So when you first hook up to a topic, you don't have any historical data. You have to ingest the entire amount of the table. This is really, really hard. This is a lot of data. But once you get past this and you're in steady state was really, really easy. So the initial compaction was really tough. Maybe it could even take like a day or two to actually compact, but after that, we're able to do things really, really fast. The second one was that we could kind of divide our tables into two different categories. So I mentioned that we're streaming these data files and delete files, and then I'm rewriting them periodically, maybe every hour. So you have this section that we call the uncompacted zone. So where like the updates haven't been applied. They have to be figured out at read time by the engine. And for some tables, querying this uncompacted zone was really fast, and for others, it was really, really slow. So what we had to kind of do, and moving forward, what we're going to have to do is figure out maybe there's some concession here that we have to make of holding back updates until the rewrite has actually taken place. So that introduces an extra complication into our pipeline. And finally, like really aggressive rewriting. We have to constantly rewrite the data files on disk. So we are really happy with the results. We're really happy about the performance. We're really happy about having more levers at our control. I mentioned the fast and slow uncompacted tables. And I just want to highlight here that it's because of Iceberg's abstractions that we're able to actually do all of this. It abstracts the way data is written to disk. And it's because of all of this that we're able to do these very, very targeted rewrites and get the performance that we ended up getting. Even though there was increased complexity of building the streaming pipeline, for us, this was totally worth it to have more accurate data, but also to be able to produce updates as soon as possible to the data platform. So in some cases, we could produce updates in 15 minutes, where our old platform, maybe only every 6 hours, were we producing a new version of the table. Thank you, everyone.
Thank you so much, Vicky, for the talk. Now, are you ready for some questions?
Sure.
Great. We're going to start with the few upvoted ones first, and then we'll let you pick the questions towards the end. Let's look at the first upvoted one. If we need to delete the data for compliance reasons, is positional delete considered a violation?
That's a really good question, because technically the data is still written to disk. So what I would urge you to think about is, what is your timeline? What's the life cycle? So for us, when we do a rewrite, we're rewriting the data completely on disk. I kind of skimmed over a lot of the details of Apache Iceberg, but one of the things that it gives us is a ledger. So we can actually see all the different transactions that have happened to the table, how it's evolved over time. And in a case where you want to permanently delete something and you want to make sure it's removed from disk, what I would say is you want to perform the update, do the rewriting of the data on disk, and then remove any transaction or any commit to the table that is actually referencing those positional deletes. And then once you do that, then you can slowly clean up the data on disk itself. So there's a lot of moving pieces here, but positional deletes alone this data will still be on disk. So you have to make sure that you have everything in line to make sure you actually do the rewrite and clean up after yourself.
Great. Have you checked the use of Avro format instead of using Parquet?
So we haven't looked into Avro that much. Avro is not, it's a schematized data format, but it's not a columnar format. And the reason that we use Parquet, or I know some people use Orc, they're both columnar formats. The benefit is that at query time, usually a data scientist, someone executing query, is only interested in a subset of columns. So it gives us the power to skip huge chunks of the file that we're not interested in. So that's why we use Parquet. That said, Iceberg does utilize Avro for all of the metadata. All the metadata is actually written in Avro format. But the actual data files on disk, we're keeping everything as Parquet.
I'm going to do my best with this next one. Does enabling bin log on MySQL affect RDS performance? And 2, for companies of smaller size, what is the go-to way to ingest RDS database data into S3, for example?
Okay, so the first one, does enabling bin log on MySQL affect RDS performance? Yes, it does. So the way that we hook up to our MySQL database is we have a read replica. So it's not affecting like production queries. We have a read replica. Even back in the days when we did the statement-based replication, that would also affect the query performance and operations on the MySQL database, which is why we also back then connected to the read replica. So it does have an effect. It's not huge. It's significantly less than running queries, of course. Okay, number 2, for companies of smaller size, what's the go-to way to ingest? So I know that there's some companies offering like out-of-the-box tools to connect to your MySQL database or Postgres database, whatever your RDS database is, and to collect and emit these events. I think even Google is working on something where, like, if you use Google's cloud SQL databases, you can automatically get all the bin log events to what's their data bus, event bus, PubSub. You can get all the events to PubSub, but we had to do all of this because of like the very, very complicated nature of how the databases are managed at Shopify. But this, yeah, for a smaller company, I'm not sure what those companies are, but there's definitely services that will do most of this for you, at least getting the events out of the database and onto like some sort of like queue.
Great. What business value did unlock by reducing latency down so drastically?
So there's a couple use cases. Maybe one that I'll focus on is fraud. So fraud detection is something that happens like in maybe not real time, but near real time. And even though the fraud teams at Shopify would have their own streaming pipelines to identifying things, their staff still wants to double check things manually after the fact. So if we have these table snapshots that are being updated every 6 hours, they get really, really frustrated that the production DB is just different than what we have in the data lake. So that's why it's really, really important for them to have these really fast updating snapshot tables.
Very good. Can Apache Iceberg be used in AWS architecture?
Absolutely. And actually, they kind of have some built-ins for AWS specific things like Glue. So Glue is their like AWS's managed Hive metastore. So Glue can automatically connect to Iceberg and things like that. So yeah, you can use it. I'm sure there's some other things that you'll have to do to get it all set up, but you can absolutely use it on AWS.
Great. How does Iceberg differ from Delta tables?
So I'm going to guess by Delta tables you mean like Databricks' like Delta Lake and that product. So it's basically the same product. It's very, very similar. I think maybe Databricks, a lot of their newer features are behind a paywall, so you'll have that vendor lock-in. At Shopify, we want to be as open source as possible, which is why we went with Apache Iceberg instead of Delta Lake. And I think there were like some issues with Delta when it came to like concurrent update operations. But these are like really small implementation details. But under the hood, it's essentially like a very, very similar, almost one-to-one product.
The next one is reading Iceberg tables, meaning you don't have to connect to Hive Metastore, right? How is this affecting performance? What is your experience?
So actually, I kind of glossed over this as well. There's a lot of moving pieces to just even how Iceberg works. So the key to Iceberg is that it wants to offer like atomic transactions, and you need something to provide that atomicity. So for us, our catalog is a Hive metastore. So we do connect to Hive, and we register our tables in Hive. And if you want to produce an update to an Iceberg table, you have to contact Hive, grab the Hive lock, do the change, and then release the lock. So Hive is giving us that atomic operations to our table. Now, you don't have to use Hive. You can use something else as your catalog. So out of the box, you could use it with HDFS, and it can just use files to provide this. You can't quite do that when using an object store like S3 or GCS. Like we're fully on Google, so we use GCS because object stores don't have atomic updates or copies. But you can use something else. You could even use like a relational database, just like a vanilla like MySQL database. Like you can use something else to be your metastore or your catalog. But you have to, the important part here is that you have to have something to give you the atomic transactions. So the other part was, how is this affecting performance in your experience? So Iceberg tables are super lightweight. So I know people have problems with Hive, especially when they're registering tons and tons of partitions in Hive. Now, Iceberg, all it's doing and storing in Hive is like a pointer. Maybe I can go back to my slide deck, and I can kind of point this out. I have a lot of slides. So what's stored in Hive is just this kind of pointer to the metadata file that is the ledger for your Iceberg table. So basically, that's the only thing that's stored in Hive. All of the data about the data files, the partition information, all of this exists as metadata files on disk itself. So it doesn't actually affect Hive performance. Hive is not like a bottleneck when it comes to like partitioning and stuff like that. For the read perspective, it's quite good because everything is super lightweight. Where Hive could become a hindrance is when you have tons of concurrent writers. So everyone wants to publish and do updates to Hive. So we have this problem because we have a streaming pipeline. We have a writer, independent writers for each of our Kafka partitions. Some of our topics have 500 plus partitions. That means 500 plus writers who all want to commit to the table at the exact same time. So we had to build something to actually aggregate those like requests to commit and update the table. So that's one place where we did see a bottleneck. So we had to build like a separate piece of infrastructure to handle that problem. But that's very specific to like our scale. Yeah.
Okay, great. Time for a couple more. How do you handle cascade deletes in the source tables using Debezium? Did I say that right?
Debezium.
Those don't make it to the bin logs.
Oh, I'm not aware of this problem of like cascading deletes. So whoever asked this question, I'd be interested to hear from you afterwards, and maybe we can talk about Debezium. My team doesn't actually own the CDC collection part. We own just we're consumers of the events from Kafka. There's another team that is responsible for CDC and Debezium and collecting those events. So I'm interested to hear if like you've ran into this problem and if you could explain it to me a bit more.
Okay, good. Have you considered solutions other than Parquet plus Iceberg? If yes, what were they and what made you choose this one over the others?
Yeah, so there's a couple different technologies. We already talked about Delta Lake a little bit, so that's a product by Databricks. The other one is Hoodie. Hoodie is very similar. That came out of Uber. I mean, I think we looked into Hoodie a little bit, but this was maybe in 2017, and it just wasn't there in terms of what we wanted. Like, I think Hoodie, the problem was it was very like time-based, at least at that time. So if you have to partition your table by time, that doesn't really work for our use case, because you could have a table where, say, a merchant is updating a product description, right? That original product description could have been written 2 years ago. That means you have to go into the partition from like 2 years ago. So we ended up in the situation that it looked like we had to touch all the files anyways, so it wasn't a big benefit. Maybe Hoodie has changed since then, but we've kind of doubled down on Apache Iceberg.
Great. We have time for one more. Vicky, would you like to choose the last question? Okay, maybe this latest one. From the ingestion point of view, the backfill is critical. With the streaming CDC, could not be a problem to run a backfill. So yeah, backfilling is critical, especially you can imagine we schematize all our data, and when there's a breaking schema change on a core table, like a database table that we're running, basically we don't know how to evolve our tables that we've previously collected and built. We have to do like a whole backfill. This is a very expensive operation, but it's also a very critical one. And we have negotiated with like our CDC team so that they will like do complete backfills. But what we're trying to really push for, and this is more of like a political answer, is that we want to, what would be great from my point of view is if our application developers stop doing breaking schema changes. Right? Like that would help me like immensely. Because backfills are so expensive. And what I'm trying to do and what my team would love to do is to communicate how much work and effort it is to perform these backfills. I want those application developers to feel that pain and to maybe like make us go into a world where if you do need to do a breaking schema change, maybe roll over to a new table and we can start ingesting that table. So we get all of the events naturally. But yeah, breaking schema changes are really hard, which forces us to do backfills, which are critical. It takes a lot of time to re-ingest full tables. Yeah, it is a problem. Vicky, thank you so much for being with us today. Big round of applause for Vicky, everybody.